Good afternoon, everyone. Welcome to the AESP Converging COVID-19, Environment, Health, and Equity. My name is Maya Trotz, and I am the principal investigator of this conference, along with Dr. Colleen Naughton. And we're so happy that you're joining us today. So as we go into section 2, which is COVID-19 and fostering informed decisions and actions. Some notes before we start, that our webinar is being recorded, and by continuing to view the webinar, you are consenting to being recorded. Some notes on viewing this properly. We do have sign language interpretation. And for that, if you go to the right portion of your screen and you do side-by-side view, you would be able to see the speaker and the interpreter. Some of you may also have a drop-down menu from the top of your screen where you can, on the top of your Zoom screen, and from there you can see the side-by-side view also. Now, we also have a Q&A session, a place where you can enter questions that would be asked during the Q&A section of today's presentation. But we also have closed captioning if you need that service, and you can just click on the icon at the bottom of your screen. And now I'd like to play a welcoming video on the conference.
The Association of Environmental Engineering and Science Professors, AEESP, is made up of professors in academic programs throughout the world who provide education in the sciences and technologies of environmental protection.
As hard as we work in our domain expertise, we need to work equally as hard to build positive human relationships with our colleagues, our students, and the communities that we serve.
We will continue to work towards a more just, equitable, and healthy society.
The goal of the virtual conference, Converging COVID-19, Environment, Health, and Equity, is to bring together different disciplines of environmental engineering and science to discuss actions to form a more healthy, just, and equitable society.
The conference themes align with the National Academy of Science, Engineering, and Medicine's grand challenges for environmental engineering in the 21st century. And they are
COVID-19, systemic biases, and environmental engineering and education.
COVID-19, fostering informed decisions and actions.
COVID-19 and the creation of efficient, healthy, and resilient cities.
COVID-19 and sustainably supplying food, water, and energy.
COVID-19 and designing a future without pollution and waste.
COVID-19 and climate change mitigation and adaptation.
Each session, as much as possible, will look at the convergence of air,
water,
wastewater,
food,
people, the built environment,
waste, fostered by the COVID-19 pandemic, and the unfolding realities of the need to address inequities in our communities.
Faculty from the University of South Florida and the University of California, Merced, are pleased to hold this virtual conference with support from AESP and the National Science Foundation's CBET program. It is my pleasure today to introduce Dr. Amy Stewart, who's a professor of at the University of South Florida, where she leads the Environmental and Occupational Health Concentration and is president of the Faculty Assembly of the College of Public Health. Dr. Stewart is also a colleague of mine in the Department of Civil and Environmental Engineering, and she has an appointment in the Center for Urban Transportation and Research. Her research focuses on air quality systems modeling, and she leads initiatives related to air pollution exposures, environmental health, and urban sustainability. Dr. Stewart will be the moderator of today's session, so handing it over to you.
All right, well, thank you so much, Maya. It's really a privilege to be here. So today I have the privilege of moderating the discussion on the theme of COVID-19 and fostering informed decisions and actions. So when the National Academies published the Environmental Grand Challenges, they couldn't have foreseen the COVID-19 pandemic would roar in and highlighting the real urgency of this challenge. Over the past 6+ months, we've all experienced the need for better information for decision-making at all levels, from our own personal daily decisions on whether and how to send our kids to schools or to protect our laboratory workers, to the actions of state and national and global leaders who must address the acute and long-term challenges of saving lives in this pandemic. In addition, COVID-19 has brought into sharp contrast the inequities that pervade the health outcomes of environmentally related decisions, further highlighting the need to consider the distributional aspects of all that we do. So the Academy's focused on a few things in describing this environmental grand challenge. These include, first, equipping people with information and solution options needed to make wise choices. Second, ensuring that experts work and act in partnership with other stakeholders and with communities so that decision makers at all levels can understand, can evaluate, and can trust the information available to make those choices. And finally, the need to consider equity and the distribution of impacts among individuals and among groups in all of our solution advances and interactions. So the role of our AEESP community, in other words, academic environmental engineers and scientists, are manifold. We traditionally have contributed and continue to contribute to developing new approaches, technologies, and data that are needed to address specific environmental technical problems and science gaps. We also work as integrators across technical and social fields to design solutions that consider the complex, interacting human, natural, and built environmental systems. The academies now challenge us to build new skills that allow us to get more involved in directly informing decisions, actions, and policies. This includes developing and improving decision support tools and technology-enabled platforms that synthesize information across fields and can directly examine potential policy actions. But it also includes working in collaboration with stakeholders, particularly those from marginalized communities, through participatory science approaches that build understanding and trust and lead to effective and sustainable solutions and policies. In the talks that we have here today, we'll be hearing from several of our number who have stepped up to the call of fostering informed decisions and actions related to the COVID-19 pandemic. This includes work on virus aerosolization, impacts of HVAC systems, aerosolized virus collection by masks, impacts of surface characteristics and flow dynamics on virus transmission, effects of waste collection and treatment, and measurement of exposures, dose, and risk. Our speakers today will be discussing the findings from their research on these topics, but they will also discuss how they've expanded their horizons through interactions that have brought that research to decision makers at multiple levels to directly address the Academy's challenge of fostering informed decisions and actions. So please welcome our speakers today, who are Lindsay Marr, Colleen Naughton, Yang Wang, Shamia Hoke, and Chuck Haas. Thank you all for agreeing to talk with us today and to share your experiences. I'll be introducing each of the speakers in turn before their 5-minute mini talks, and then we'll have hopefully a lively discussion over questions after that. All right, so let's get started. Let's start with Dr. Lindsay Marr, who is the Charles P. Lunsford Professor of Civil and Environmental Engineering at Virginia Tech. Professor Marr's research considers the interactions of nanomaterials and viruses in the atmosphere. During the COVID-19 pandemic, she has been studying how SARS-CoV-2 and other airborne pathogens are transported in air. She has also actively engaged with the press and social media to disseminate her knowledge and experience. This has included an impactful New York Times opinion piece on the virus's transmission in air and an interview on NPR on how to lower risk of transmittal, as well as many quotes in the press. Professor Marr studied engineering at Harvard University, graduating summa cum laude. She moved to UC Berkeley for her graduate studies in environmental engineering and joined MIT, working alongside Maria Molina for her postdoctoral work. Please welcome Professor Marr to speak with us about what happens when you open your mouth.
Thank you very much for the introduction. I'm not able to start my video because the host has stopped it. So if you'd like me to show up, if you want to allow that, I can start it again. I'll go ahead without that. I'll be talking about what happens when you open your mouth. Okay, here we go with the video. Great, next slide, please. So to begin with, we know that the virus is being transmitted through the air, and it's important to realize that the airborne virus is not naked. We do not have naked with any pathogens, bacteria or virus out there in the air or on surfaces. The virus is embedded in a respiratory droplet, which contains additional things besides water, which I'll talk about in a minute. And it's the size of this droplet or aerosol that defines its transport, not the size of the virus itself. So the virus itself is 0.1 microns. That respiratory fluid droplet carrying it could be anywhere from 0.2 microns to 100 microns or more. Next. The images on the right show what dried respiratory droplets look like. Those are electron microscopy images. And you can see on the top one, that outer kind of ring shows probably the initial diameter of the droplet. The water evaporated, leaving behind that crystalline solid, which contains potassium, calcium, chloride, carbon, and sulfur, things that we would expect to see in the salts and organic components of the droplet. The pie chart on the right shows what the droplet is, what those non-volatile solids are. There are a lot of sodium chloride and some other salts. There's protein that can be anywhere from 1/4 to the majority of those solids. There's some surfactant. The virus itself is far less than 1% of the solids. Next. When we talk, we produce aerosols. So we know that when we cough, we produce large droplets and some smaller aerosols. But when we just talk, we actually release a plume of aerosols. This is nice work done by Lydia Moroska in Australia, showing the size distribution of aerosols and larger droplets that are released when we speak, shown in the top panel, and when we cough, shown in the bottom panel. Notice that both the X and Y axes are shown in log scale, and there are more like 3 modes. The first smallest two modes are kind of, they overlap. So if we look at the speaking distribution, the black dashed line, you can see that there's a peak around 1 to 2 microns. This is for the droplets and aerosols right as they come out of our mouths before they have undergone any evaporation. And there's a little bit of a shoulder out there towards maybe 4 microns or so. And then there's a larger mode of these larger droplets. These are visible ones that is centered around 100 to 200 microns. Those only make up 1% of the total number of droplets and aerosols that we release, whereas 99% of them are in those smaller sizes, mostly less than 10 microns. Next. Now, if someone is infected, these aerosols may contain viruses. And when we speak and we say a phrase like "hello world," we release about 5 nanoliters worth of liquid. And if you have a kind of average load of viruses in your respiratory fluid, you might release 30 viruses in terms of the number of RNA copies of it. When you cough, you release a much larger amount of fluid. Because there are some large droplets, that would be 125 nanoliters and close to 1,000 viral RNA copies. Next. And this is why it's so important for us to cover our mouths. Source control means, just in traditional air pollution terms or water pollution, you go back to the source and reduce the amount that it is releasing into the environment. It's almost always much easier to do that than to try to clean something up or reduce its concentrations after it's been released in the environment. So the person here on the left is speaking and releasing maybe one large droplet and 100 to 200 aerosols, those little red dots. And what we're going to do is we're going to put a mask on her. Next. All of a sudden, we have blocked those large droplets and aerosols from getting out into the air. And now they can no longer spread in the air or build up in the air. So that is why masks are important. And Dr. Wang will be talking about that after me. Next. So I started opening my mouth about this topic early on in the pandemic because I've studied airborne transmission of viruses for over 10 years. It was evident to me that airborne transmission was important for this virus, and I knew there would be a lot of misinformation, panic, and fear and inaccuracies in how people talk about airborne transmission. So early in March, I tweeted out, let's talk about airborne transmission of SARS-CoV-2 and other viruses. A discussion is needed to improve accuracy and reduce fear associated with the term. Back then, I probably had about 1,000 followers, and I pulled this screenshot yesterday. It looks like I have over 26,000 followers. There's not a lot of people who have studied this question from the aerosol science side and being able to understand what sizes are important and how they move in the environment. And so to counter the misinformation, and because of my specialized expertise, I realized it was really important for me to get out there and provide the correct information. And so that's what's really driven this, to provide correct information so we can use that to slow transmission. So the main thing I keep in mind when communicating science to the public is KISS. Keep it simple, stupid. Not to imply that people are stupid, but to try to explain things in as clear a way as possible using everyday language, no specialized jargon. And if I do, to explain that and to try to relate complex scientific concepts using analogies that people encounter in their everyday life, like cigarette smoke. We can think of the virus spreading in air like cigarette smoke does. And then I learned an important lesson early on from Kim Prather, who's a professor at UC San Diego, National Academy member in Sciences and Engineering, who studies aerosols and has done a lot of communication on climate change. There are a lot of, yes, there are some uncertainties and nuances in this, but we do know enough to act. And so I took that message to heart. And yes, I could talk for hours about the nuances of various different aspects of airborne transmission, but the fact is that it's happening and we know how to slow it down. And then Dr. Stewart mentioned that I had an op-ed in the New York Times that I wrote. They asked me to write something, and it was an educational experience for me because my first draft was terrible, and then they asked me to completely rewrite it. So I submitted a second draft, and then the editor bled all over it, red ink everywhere, and it came out hopefully accessible to the public. Thank you for your attention.
Thank you, Lindsay. That's actually really interesting to hear about. Next, we have Dr. Colleen Naughton, who is an assistant professor in civil and environmental engineering at the University of California, Merced. Professor Naughton helped to lead the hashtag AESP Teach and the crowdsourcing of virtual teaching resources on a Google Sheet and on the AEESP website during the transition to online learning with the pandemic. Dr. Naughton's research focuses on designing sustainable and culturally sensitive food, energy, water systems. She recently received 2 COVID-19 emergency seed grants to conduct a microbial risk assessment of SARS-CoV-2 in wastewater for vulnerable populations, and to study adaptation of the food supply chain to the COVID-19 induced shock. Dr. Naughton has also published a perspective piece on COVID-19 impacts on waste management. Dr. Naughton received a BS in civil engineering with environmental concentration from Purdue University and an MS and PhD in civil engineering from the University of South Florida with a certificate in water health and sustainability. Professor Naughton is also our conference co-chair and a co-PI on the grant that made this conference possible. So please welcome Dr. Naughton to talk to us about what happens when you flush the toilet.
Hello, everyone, and thank you, Dr. Stewart, for that introduction. I'm honored to present to you today about what happens when you flush the toilet. As mentioned, this was part of a seed grant funded by Citrus, and it's a team effort, and I'm honored to present on behalf of my team, many of who are on this call today. Next slide, please. So many of you may be in civil and environmental engineering and know about wastewater treatment, but please bear with me. I know there's some that do not. And before I get started about what happens when you flush the toilet, in accordance with the theme of equity, not everyone in the world and even in the United States have access to wastewater treatment or sanitation or toilets. Billions in the world do not have access. But for those of you that are lucky to have access and running water, it starts with one, flushing your toilet. You may have a squat toilet and not a seated toilet. And then it goes down a pipe and into your piping system in your house, and number two, and then goes out to a sewer line or into a septic tank. And hopefully you're only flushing the 3 Ps, poos, pee, and paper. And it can travel for miles to a wastewater treatment plant in number 3, like in Los Angeles. It's a very large wastewater treatment plant. And then it goes through many steps to be treated to protect public health against diseases such as SARS-CoV-2 and other pathogens. And so it goes through chemical, physical, and biological treatment, and even disinfection with UV or chlorination before it's discharged into the environment and meets regulations such as in the ocean in LA or in other places that might be a river or a creek. Next slide. In the context of COVID-19, we've seen wastewater being used as a public health tool to inform decisions and actions through wastewater-based epidemiology. So up to over 50% of people shed SARS-CoV-2 in their feces, whether they're symptomatic or asymptomatic. And then civil and environmental engineers or scientists can collect it through the sewer system or at wastewater treatment plants. And they can sample large populations through one sample, like wastewater treatment facilities serve hundreds, thousands of people, and you can filter the sample and quantify the virus over time. There are, of course, difficulties in this process, and it should not replace regular testing. Next, please. This is not a new technique, even if the news might feel it is. It's been used for decades. It's been used for poliovirus and for opioid detection. Next. And it's being used globally since the beginning of the pandemic all over the world to detect SARS-CoV-2 in the wastewater. Next slide, please. So this is your quiz question if you're taking the quiz, so please listen if you haven't before. So SARS-CoV-2 can be used in wastewater testing, can be used as an early warning system. It's faster to process samples for larger populations. People that are asymptomatic are shedding it, and people at the early stages of the infection before they're tested may be shedding it. So it can be anywhere from 3 to 14 days before shedding. And this is an example from Yale University, and they have a great website. Next. You might have heard University of Arizona used wastewater to detect an outbreak before it started. And next. And cities, Ottawa, there's been a lot of talk on Twitter about the increasing concentrations in Ottawa's sewer. So it can be used as for individuals. They see concentrations increasing. They know they need to physical distance more, use masks. Public health departments, states, cities, and countries are using this to implement measures, maybe even shut down schools or bars or restaurants to kind of stop the spread before it gets worse. Next slide. And so this is combining my two loves, the wastewater and mapping. There's a lot of dashboards available now, not in every state, but Utah has an increasing, decreasing present stoplight approach. And you can click on there to see the concentration. So increasing is red, decreasing is green. Ohio is the CDC and EPA pilot site, and they have tons of places they're monitoring throughout the state. And a lot of websites just show the concentrations over time. This one's showing with our third surge that we're seeing in the United States. We're seeing that in wastewater as well, like in Massachusetts. And Tempe, Arizona also has a great dashboard as well. Next. So our group is trying to foster informed decisions and actions by putting this all in one place. We were inspired by the Johns Hopkins University dashboard. We wanted to make a similar one for wastewater, their dashboards on COVID-19 cases. So you can zoom in on areas of the map, see if wastewater testing is happening in your area, visit the different websites and dashboards. And this is part of a larger COVID-19 wastewater-based epidemiology collaborative. The website's on the bottom right. And we also have a Twitter account at COVIDPoops19 if you want to follow that and learn more about SARS-CoV-2 and wastewater. So thank you for your time, and I look forward to questions.
Thank you very much, Colleen. I'll have to go and check out what we have in Florida here. So our next speaker is Dr. Yang Wang, who is an assistant professor of civil, architectural, and environmental engineering at the Missouri University of Science and Technology. Professor Wang's research focuses on aerosol instrumentation and measurement, aerosol cloud interaction, and functional nanoparticle synthesis. Given the COVID-19 situation and the urgent need for medical masks, Professor Wang's research lab is now testing a wide range of household materials and common commercial fabrics that can be used to manufacture masks. This work has been disseminated through a publicly available spreadsheet and featured in local and online news articles. Dr. Wang received a BS in energy, environmental, and chemical engineering, and a PhD, both of which from the Washington University in St. Louis. Notably, in 2018, Professor Yang was recipient of the GAEF PhD Award by the European Association for Aerosol Research for his dissertation work. Please welcome Dr. Wang to discuss what information to share with people on mask making materials.
So hello, everyone. During this talk, I'm going to share some information on mask making materials. So first, I would like to thank the students in my group who have been working tirelessly to provide the data that are shown in this presentation. Next slide, please. So during the pandemic, due to the shortage of the medical PPE, for example, N95 respirators or surgical masks, people are always looking for the best material for their homemade masks. But before we identify these best materials, we need to first understand what are the criteria for a good mask. So FDA and CDC actually gave their recommendations on these criteria, and they include filtration efficiency, fluid resistance, flammability, and biocompatibility. So among these four, the top two are very important because the filtration efficiency determines how effective the mask is in removing the particles, and the fluid resistance determines how easy it is to breathe through the mask. And as for our homemade or DIY masks, we also need to make sure that they also satisfy these criteria, or at least the top two criteria. And here I have to mention that during the early stage of the pandemic, Missouri S&T teamed up with our local hospital, Phelps Health, and formed a joint task force to evaluate a wide range of household materials in their filtration efficiency or filtration performance. And I think this is a very good demonstration of how environmental engineers can help with our local community to alleviate the impact of this disease. Next slide, please. And in terms of evaluating the performance of these masks, they generally include two aspects. So the first aspect is on the material test, which means that we need to cut these materials into discs and fit them into the filter cassette, and we can evaluate its filtration performance. And the second aspect is the fit test, which means that we need to manufacture these materials into the entire mask and further evaluate its performance. And here I want to mention that the fit test is equally important as the material filtration testing, because the air leakage may also lead to the transmission of the disease. And we can use a wide range of aerosol instruments to conduct these measurements. Next slide, please. So the general method we can use is if we know the concentration of the aerosols upstream and downstream of the masks or the materials, then we can efficiency and also the filtration efficiency of these materials. And of course, the filtration efficiency is a strong function of particle size. For example, the N95 respirators are evaluated at a size of 0.3 micrometer. And as for the SARS-CoV-2 viruses, more and more evidence is showing that these viruses are actually carried by larger aerosols or droplets, for example, larger than 1 micron. Therefore, their filtration efficiency is strongly dependent on their different particle size. But in general, these efficiencies are positively correlated with each other. Next slide, please. And here it shows a list of fabric materials that we have tested in terms of their filtration performance. And I'm showing the filtration efficiency at 0.3 micrometer. And these fabric materials generally include cotton, wool, silk, polyester, and so on. So the general pattern we found from our result is that the denser fabrics will have higher filtration efficiencies. And in the fabric industry, people normally use the parameter called the grams per square meter, or the GSM, to describe how dense the fabrics are. And an easy way for us to tell how dense our mask is try to see whether we can see light through the fabrics. And if we can't see the light through, then it means that the fabric is not dense enough. So we have to stack multiple layers to boost up the filtration efficiency. But we also need to make sure that there's no air leakage. And we can test that by checking whether we will blink or whether there will be fog on our glasses when we exhale as hard as we can. Next slide, please. And among all the materials that we have tested, we found that the fibrous materials, which are generally the materials that contain electrolyte inside, have the best performance. And these materials generally include air filters, furnace filters, and so on. So for the figure on the left, it shows the material's filtration efficiency as a function of the fluid resistance. In general, the better materials would have a higher filtration efficiency and a lower flow resistance, which means that their data points should be on the lower right corner of this graph. And you can see that a lot of these better materials starts with the letter H in front of them, which means that they are household air filters. So this result means that we can use these air filters as an insert for our fabric masks, but we also need to make sure that the air actually goes through the filter, and we do not recommend washing of these masks. So finally, just one slide before. So by the way, if you wear a face shield when you go to the classroom, please also make sure that you also wear a mask, because our study also found that when you walk around, the aerodynamics might work against you by entraining more particles into your inhalation zone. So next slide, please. So finally, I'm listing a few helpful publications, workshops, websites, and Twitter accounts to follow. And I think during this pandemic, you really have to appreciate a lot of environmental engineers who are actively sharing their research results and also their understanding of this disease. And specific for this talk, I want to thank Dr. Lindsay Marr and Dr. John Walkins, who provided their comments to these slides. So that's all for my presentation, and thank you all for your attention.
Thank you, Jan. I think your findings about the face mask is something, not the face shield is something that a lot of people need to hear. So our next speaker is Dr. Shamia Hoke. Dr. Hoke is an assistant professor of civil and environmental engineering at the University of South Carolina. Her research interests are on the development and application of mathematical models for fluid flow, pathogen dispersion, and decontamination in the environmental system, with the objective of informing risk assessors and first responders. Professor Hoke's recent studies have involved multi-physics modeling that applies computational fluid dynamics analysis and neural networks to predict bioaerosol transport and inactivation in indoor areas. Professor Hoke's work to model COVID-19 transmission was featured in her area's local news from early in the pandemic. Dr. Hoke received a PhD in environmental engineering from Drexel University under one of our other speakers, Chuck Haas, a Master's of Applied Science in Chemical Engineering from the University of Toronto, and a BSc in Chemical Engineering from Bangladesh University of Engineering and Technology. Please welcome Professor Hoke to speak with us about the influence of surface characteristics and flow dynamics on SARS-CoV-2 transmission.
Thank you very much for that introduction, Amy. And good morning and good afternoon to everyone who's watching from wherever you are. This is a collaborative work across the field with professors at Department of Chemistry and Biochemistry at USC and with collaboration with Ohio State and Michigan State University. Next slide, please. So we have heard about aerosol transmission and about its release in the atmosphere, in the bulk air, and in our indoor spaces. I'm going to actually focus on how we can take those decisions so that we can actually build spaces which are safe and healthy for us. A virus, which as we just heard, once it's released in a droplet or in something inside, it's never released on its own. Once it's released, it will travel in the bulk air and find its way somehow or the other to the surface. In the middle of it, there would be the boundary layer which demarcates between the bulk air and the surface. Once it reaches the surface, it will interact with that surface depending on the properties, and subsequently it may remain attached, or depending on maybe activities which could cause it to resuspend back into the bulk air. Next slide, please. So first, we're going to take a look at what happens if there is an interaction with viruses and surfaces. And these experiments were conducted using a vaccinia virus, and the intent is to move on to lentivirus, which is a model for SARS-CoV-2. And this work has been funded by the USC Emergency COVID-19 Fund. We looked at what would happen if we passed vaccinia virus and allowed it to deposit on different kinds of sensors using a very sensitive microbalance, the QCMD approach. And subsequently, we tried to find out what would happen if we tried to wash out that virus using different flow rates. Next slide, please. So the experiments was done with multiple surfaces, and we have here glass, silica, gold, and stainless steel. We are continuing our experiments with copper surfaces, as well as with measles virus. Current results have shown us that stainless steel stands out when it comes to having a high mass absorption onto the surface. And then when we subsequently try to wash it off, we have stainless steel, which actually holds on to the virus, as opposed to glass, which allows the most washout, followed by silica, gold. And atomic force microscopy has shown that this is mainly due to surface charges, both belonging to the virus as well as the stainless steel. So what this kind of tells us that as we go through and try to understand how this transmission happens in our environments, we can look at these different surface properties and see how they interact. And this gives us an idea of what to choose when we go ahead and try to design or inform the materials we use in our day-to-day life in our built spaces. Particularly, please go to the next slide. Particularly if we now focus on bulk airflow. So currently this picture that we just had looked at desk shields, right? Currently, all our children are going to schools and we have desk shields as one of the protective measures. So the question that might come out is, are those desk shields effective? And what would make them more effective, or whether or not we need to think about materials or where they are located. Next slide. So these are computational fluid dynamics simulations, which try to look at detailed airflow modeling on where the air travels and where particle travels. I have one desk shield and two sources of sneeze, one at a child's breathing level and the other at an adult's breathing level. The second plot shows actually a plot of velocity magnitude at different locations in that room. And while we have low velocities across the room, if you notice, just behind where the desk shield is located, there is a slightly higher velocity compared to the rest of it, which indicates that, which was not there when the shield was absent, which indicates that the presence of the shield immediately makes changes or disrupts the pattern in which the air flows into that room. Next slide, please. So we assessed what would happen if airflow and sneeze direction were altered. So the red arrow indicates that the airflow is in the room is in the opposite direction to the sneeze. The black arrow indicates that the sneeze is in the direction of the airflow. So if you look at the two plots at the top, which is red bordered margins, where we have the flow of the sneeze in the opposite direction to the airflow, incorporating a partition reduces the time of exposure, the total number of particles inside the room, from around 8% to 3%. The green line is when the sneeze occurs from the adult, and the purple line is when the sneeze occurs from the child. Now, if we go down to the plots below those two, where we have the black line, which is the sneezes occurring in the direction of the flow, you will notice that the presence of the partition actually causes more particles to stay inside the room, as opposed to when there is no partition. And the case gets worse for the child who's sneezing and who has the shield in front of him or her. So it goes from nearly 0.02% to around 4.3% remaining after around 15 minutes. Next slide, please. So we focused at the worst case scenario to take a look at what's happening to the particles overall and tracked their changes over a 15-minute period. And without the partition, if you notice, that's the second plot, most of the particles have already moved away after 1 minute, which has not happened in the case for the first when we have the partition. So this reinforces the fact that we have to take into consideration not only the fact that someone is sneezing, but also when we make design choices, what the airflow conditions are within the room. That way we can make an informed decision on designing so that we actually consider the fact that airflow would influence the pattern in the room would be influenced due to the way we have designed our indoor spaces. The surfaces also, if we have the desk shield made in certain surfaces, we could learn more about how different materials would influence that interaction with those droplets which are being released and possibly interacting with the surfaces. Next slide, please. So finally, I just want to focus once more that this particular pandemic has highlighted how much multiple disciplines must come together and work together. This particular slides I put together involved fluid dynamics, aerosol physics, and surface chemistry, and needed input from multiple disciplines. It's not a one-size-fits-all approach. We have to be open to the fact that multiple designs we have to look at different ways that things could actually make changes. Solutions do not have to be expensive. We just have to figure out how we have to make that solution with our information that we can get from our research, which can actually transform how we design buildings. And this can also lead to us learning how to actually design safe, healthy, and affordable buildings that can support equity in design and construction. Thank you.
Thank you, Shamia. It makes me think twice about all the fancy stainless steel appliances in the kitchens these days. Our final speaker is Dr. Charles Haas. Professor Haas is the department head and L.D. Betts Professor of Environmental Engineering in the Department of Civil and Architectural and Environmental Engineering at Drexel University. His research focuses on the treatment of drinking water. Specifically, Professor Haas has studied chemical disinfection processes, inactivation of emerging pathogens by disinfectants, and the use of computational fluid dynamics for process modeling. Dr. Haas is also an expert in risk management and industrial waste treatment. Professor Haas has an online blog where he has shared some of his expertise and experience as it relates to the COVID-19 pandemic. In addition, his quick development of an engineering class on COVID-19 at the beginning of the pandemic was covered in the press. Dr. Haas received a BS in biology and an MS in environmental engineering from the Illinois Institute of Technology. He earned a PhD in environmental engineering from the University of Illinois at Urbana-Champaign. Notably, in 2017, Dr. Haas received the National Water Research Institute's Alethea Richardson Irvine Clark Prize for Excellence in Water Research. Please welcome Professor Haas.
Thank you, and thank the organizers for putting this together. So I want to take a high-level overview of the problem of COVID-19 from a risk analysis point of view and point out the connection with some very basic concepts that we use in environmental engineering throughout our realm of research and practice. Next slide. So one of the broad concepts that we're used to dealing with is the source transport receptor paradigm, the idea that we have a source of contamination, in this case, microorganisms into the environment, such as by speaking, coughing, or sneezing, as Professor Marr indicated. We're interested in how they might move in the environment through the air. Professor Haas covered some of this, how they may survive, how a susceptible receptor becomes exposed, either by touching a surface that's been contaminated, the fomite route, by close contact where large ballistic particles impinge on the nose, eyes, or mouth of an individual, or by inhalation of the smaller particles via airborne inhalation. Next slide. So the broad framework that I've used to approach these and other problems is the risk analysis paradigm. And it proceeds from the same considerations that we do for any environmental contaminant. We define the hazard. We look at a dose-response relationship. We define the exposure, perhaps by a source transport receptor model. We combine dose response. We get to a risk characterization. That leads us to proposals for action after considering other factors such as economics, political concerns, social concerns, or other technical data. Now, one key piece of information that we do need is a dose-response relationship. And on the right-hand side, I've just put up a graph from a paper that we did about a decade ago on the first SARS coronavirus outbreak, where we showed that we could develop a dose-response relationship for that virus. And at this point, these dose-response curves are really all that we have to base our analysis of risk for SARS-CoV-2. Now, just one editorial comment on this. For those of you who follow my Twitter feed, you see one of my pet peeves is that in the microbiology and medical literature in particular, there's still this outdated concept of minimum infectious dose. And the bottom line is there is no point at which the average dose administered to a population results in a risk of 0. So there is no threshold, there is no minimum. And in fact, for all organisms, including the coronaviruses that we've looked at, there's a concept of low dose linearity. Next slide. So if we consider how we might control the risk from coronavirus 19, or SARS-CoV-2 rather, the risk of COVID-19 illness, we can take a page from the industrial hygiene literature, which talks about the concept of hierarchy of controls. And by the way, we've also used this in the hazardous waste field in a related concept. We could eliminate the hazard, and in this case, until we get an effective vaccination, elimination is off the table. Substitution is not applicable, but there are engineering controls that we can employ, such as ventilation, physical barriers, de-densification of rooms, and so forth. There are administrative controls, working from home, staggering schedules. And finally, at the bottom, although important, it tends to be the option of last resort, personal protective equipment, masks, respirators, and gloves. Now, this industrial hygiene model has limitations, and I think what's rapidly become clear in the context of COVID-19 is something, again, that environmental engineers have known for a long time. Next slide, please. So as the introduction said, I spent a lot of my career looking at drinking water quality, drinking water safety, and wastewater reuse for potable and non-potable uses. And we talk very often there about the use of multiple barriers. Another term that's been used is layered protection. But this graphic, which is called the Swiss cheese model, I think is a good communication tool for the lay public, which explains what we're talking about. So there's no single thing that we can do in and of itself that would be 100% effective. But the concept is that if we combine multiple barriers, multiple factors together, multiple slices of the Swiss cheese, the holes will not overlap. And so ultimately we can get highly effective protection by combining sufficient numbers of these relatively independent barriers, such as physical distance, ventilation, masks, hand hygiene, and so forth. Next slide. Now, the real challenge, and this is my last slide, is how do we get the population to employ multiple barriers? And I think this is the challenge where environmental engineers need more information from social science. How do we get adaptation? How do we communicate how to reduce the risk? And actually, there is expertise in this area, and there are a variety of elegant techniques to try and lower the disconnect between what we know technically about risk reduction and what the public can comprehend and can operationalize with respect to putting those factors into play. And I think clearly this area in the context of COVID-2 is something that we really need more information on. So with that, that's my last slide, and I look forward to the questions.
Thank you, Chuck. Yeah, this whole good reminder of the multi-factor control being very important. So now we want to have a discussion related to the theme, particularly of fostering informed decisions and actions. And I'll start with some overarching questions for the entire conference series. So these questions are for any of you to pop in and answer, and so I'll just let you do that, and or if there's a blank space, then I'll call on individuals. So the first question is, what role does equity play in your research and teaching? And how do you incorporate equity in your research and teaching?
So in the risk context, I mean, we always talk about sensitive or susceptible subpopulations, and those could be by virtue of differential exposure or differential inherent sensitivity. For COVID-19, we don't know a lot yet about intrinsic sensitivity, although there are some speculative threads, particularly in the preprint literature. But we do know about venues that may result in higher exposure. And so, you know, we need to understand how to characterize them better. And I should say venues and activities.
Thank you. And the rest of you, Lindsay, have you thought about this issue in your work at all?
Certainly in my teaching, we address air pollution problems in the developing world, which is where we see some of the highest levels of pollution, and also in kind of industrial areas in the US, near roadways and indoors where, for example, the buildings have mold problems.
I know, Colleen, you do a lot with equity in your work. Do you want to say?
Yeah, oh, go ahead. Yeah, for our research, we definitely try to incorporate equity as much as possible. For the wastewater research, Dr. Kinua at UC Davis is doing a QMRA. Thanks, Dr. Haas, for all your ground laying and that methodology. And we're doing a survey right now to wastewater treatment workers, seeing what their underlying health conditions are, pre-existing conditions, since they are exposed to contaminants at the wastewater treatment plant. Not to scare anyone about getting SARS-CoV-2 from wastewater, that's a very minimal exposure route, but for people that are more exposed, we do need to consider it. And then also we're looking at communities that are close to wastewater treatment plants. And we've seen in the literature before that like landfills or other toxic waste sites are generally located in lower income and minority communities. So we are doing an analysis to see if that's the same for wastewater treatment plants in California. Not finding it overall for the state, but in urban areas, they do tend to be in more disadvantaged communities so far. And I do try to incorporate equity a lot in my teaching, just doing different modes of teaching, active learning, flipped classroom, since everyone's a different type of learner. It's a little challenging in the virtual environment, but I'm learning. You see, I share my pronouns and my name to respect different gender identities. But still trying to learn, definitely acknowledging my white privilege and with the killing of George Floyd, and like kind of trying to address my implicit biases and learn as much as I can to be as inclusive to the students.
Thank you.
I just wanted to follow up with what Lindsay and Colleen both said about when I'm teaching students in class, we have a lot of discussion on air pollution and how it's different across countries to those who have stringent air quality measures that we have in place in US as opposed to countries which don't have it, and the results of that. We had some work done at a wastewater treatment plant of measuring pollution from the wastewater treatment plant, and the focus was on a school which was very near to it. Which is located right at the border of that wastewater treatment plant, and the consequences for the students were so close to it. And we can imagine or try to figure out the demography of the students who are in that at that location near to that wastewater treatment plant. So I guess through our research and teaching, yes, we try to address those inequalities that we end up seeing in our day-to-day work, I guess.
So maybe I can mention something about the research, especially on the experiments that we did. So I would say that Missouri S&T is located in the central Missouri, and I think there is definitely some differences from the rural to urban areas. And also, when COVID hit, there's a break of a supply chain for this medical PPE. I think the rural areas affected by quite severely. So to solve these issues, or to try to alleviate the impact, I think the approaches for different areas are also quite different. So, for example, at Missouri S&T, we formed that joint task force, or trying to find, or trying to use the 3D printing, which is the most direct way to kind of generate these non-medical PPE that can be used in these scenarios. And also, we're trying to look for the household materials that are available in this area, and then to try to alleviate this issue. Yeah.
All right, thank you. I think it's a challenge. It's important for all of our research, but it's also a challenge. So the second question related to the conference is related to the conference theme of convergence, or integrating knowledge, methods, and expertise from different disciplines and forming novel frameworks to catalyze scientific discovery and innovation. So after hearing the presentations of the others on this how could we make our research more convergent? And I'll start.
I can go if you want. Yeah, just convergence is really important for my research, as I do like food, energy, water systems. But after this panel, particularly, I learned a lot. It's still constantly learning, just from Dr. Hoke, Dr. Wang, and Mar and Haas, and we're trying to integrate risk assessment. We do wastewater. Matt Deeming, a student that's doing the research, is looking at bioaerosols and the spread from the wastewater treatment plant. So we have to look in the air literature. And I'm interested with Dr. Hoke's research with the fomites and like at the plants, and there's a lot of stainless steel there. So yeah, it's after listening, we're just constantly trying to learn and incorporate the different areas of environmental engineering and science into our research and teaching.
Well, I'd add that we had an interesting study that occurred with respect to COVID, which I know Lindsay Marr was part of as well. You know, there was a self-nucleating set of people that met on Twitter, probably 20 or 30. And, you know, one of the groups said, why don't we put together an FAQ on Google Docs? And we now have this massive FAQ. You know, I've written a tiny piece of it. Lindsay has done a lot on there. And certainly a number of other people have as well. And I think that is a good illustration of the power of social media at bringing together people from different spheres to a common purpose that I think has been good for a wide population.
Yeah, I think Dr. Haas points out a really excellent example of convergent research and dissemination and broader impacts, because this document covers so many different aspects of transmission of COVID-19. No one person would be able to address all the questions in there. And we also opened it up we take feedback from people, if general public, if there's a question they want us to try to address, so they can submit it. And those kind of get compiled together. And, Jose Jimenez was instrumental. He's the one who spearheaded this. And if there's questions that come in that are, that someone else is better suited to answer, he kind of farms those out. And we find all the, the expertise to address these. And again, it's, it's this document, this really valuable resource where it's brought together a lot of different people and expertise and perspectives, where there's no way one person could have done that.
Yeah, so I think during the pandemic, this is also a time that for the environmental engineers with a similar research background to work together, because for a lot of the sampling, for example, the aerosol sampling, people may use different instruments or protocols, and they may get quite different results. I think if people can get together and then come up with the same set of measurement protocol there, then just apply them in different institutions or different occasions or different locations there, then we can get more consistent results across the country, and then get some more general understanding of these measurements.
And I'll just follow up with saying that so much of my work is on looking at fundamental principles and fundamental mechanisms. But in the recent years, I have worked with people from chemistry, public health, social sciences, and looking at perspectives from different people actually enriches the research and you answer questions you weren't really anticipating. And having worked with Dr. Haas, who was my advisor, I also learned that my fundamental mechanisms have to kind of connect to risk and how it can inform those risk analysis, exposure analysis, so that it can be disseminated to general people and we can actually use those for decision making. So those are boundaries that needs to be transcended. And I think during this pandemic, we're learning more and more how to march those boundaries.
All right, thank you. So before we move on to the questions that have come in from the audience, I just wanted to ask, indulge me with a question of my own. So what, in your work here, what has been your greatest surprise in reaching out to share your expertise about COVID-19 with the public and with the decision makers? Lindsay told us about her experience with the editors at the New York Times, which I found really interesting.
Yeah, I think another thing I've learned is that, public health officials have always associated the idea of airborne transmission with public panic, but we've presented it in a way that I think where we explain how it works and what steps you can do to greatly reduce your risk. And, I haven't detected any panic, in fact. And so, there's this kind of mantra in public health that, oh, the panic itself could be worse than the disease, but I have seen no signs of that at all. In fact, it's gone the other way around, where I think initially officials were, not providing the complete information to the public, and then the public felt misled. So that's one thing that's been an eye-opening. Just provide, as a colleague, Dylan Morris says, give the information to the public, treat them like adults.
I would also just point out, that communication is not only an issue with the public, but, in this particular problem, there are multiple disciplines that have come to the table. And I think one thing that's emerged is trigger words that are second nature to us in engineering and also folks in aerosol science that are really very inflammatory in other disciplines. And we've had, a lot of tweet wars over the past few months over the word airborne. And the concept of airborne in the medical and healthcare worker protection field is really a very inflammatory concept. But my sense is, and I don't know how you feel, Lindsay, I think we've sort of started to slowly diffuse that degree of panic in that population.
Yeah, I would agree. And I think because to the general public, airborne is something that's in the air. And if you explain how it works and everything, it's, you know, that people are capable of understanding how cigarette smoke moves, so they can understand, you know, then they can envision how the virus might move in the air and how to avoid it.
Colleen, you had something to add?
Yeah, sorry, Dr. Huss. Yeah, one of the things that I'm surprised is just seeing mayors and governors talk about wastewater treatment and get like all excited about it for monitoring SARS-CoV-2. Like, hopefully it stays that way and we stay interested in wastewater and investing in our infrastructure and using this tool. So that's been good to see. Hopefully it's not like a hype cycle and then going down in all the universities and collaborations. So then I get surprised when I talk to random people and they don't know about SARS-CoV-2 monitoring and wastewater, just because our group is so focused on it. And I feel there's been so many articles. So that's also interesting too, to get outside my bubble and see that not everyone's heard about it yet.
My interaction with teachers and students here at different school districts, and when we talk about ventilation or airflow or just general building design, I guess I'm really very impressed and excited when I see our high school students and how they interact when they hear about engineering in the context of societal impacts, you know, how environmental engineers, and we can learn about, especially for SARS-CoV-2, how we can actually come in and help in ways that I don't think high school students or middle school students think that engineers can do it this way. So getting in touch with that level of enthusiasm and getting teachers interested into it. And as I think Haas and Zamar mentioned, as well as Colleen, I think during this, because of this pandemic, we have gotten in touch with stakeholders who we may not have gotten in touch with prior to this. And their participation has been wonderful. In many ways, it has informed our research in ways that we may not have thought about prior to this.
So my biggest surprise is, so I can find that my research can be transferable to other areas, because literally before this pandemic, my research is mainly about combustion aerosols, biomass burning. And we did some previous work evaluating the performance of filters in collecting these aerosols. And then I think because of the activity that we're trying to evaluate, we're planning to evaluate these household materials, we can just use a similar setup and then apply different materials that we're interested in. And the general public is very, very interested in the data. And I think we should always try to think how our research can be transferable or communicated to the general public.
Thank you. All right, I'll turn over to Maya for one of the questions from the Q&A.
Yeah, sure. We have quite a few. And so this combines, I think, a few of them and follows up. Says, throughout the entire pandemic, a major challenge has been efficiently communicating with the general public and politicians and decision makers. And how can we reach a broader audience? And this is from Lucia R. And I think Jean McRae was along the same lines. What insights do you have to effectively communicate your work to the general audience?
Twitter has been a boon for not just us, for all scientists to communicate with the public and to get results out there on a time scale that's faster than the kind of research publication, which takes at least 6 months. And things are urgent now. It does also mean that there's less quality control without going through peer review. But if you can find trusted experts on Twitter and follow them, you can really learn a lot about what's happening, really the latest knowledge about things. So that's been an eye-opener for me to see how much science, good and bad, is happening and being disseminated on Twitter.
Well, I would also add that, for any of the professors on the audience, if you get a call from your local media and in the area that's pertinent to your expertise, take advantage of that to communicate. because obviously they are trusted intermediates to the general population.
Yeah, and to have the biggest impact, make sure you, explain it like you would explain it to your parents. Some people say to a kindergartner. So if you don't have your kindergarten, parents or kindergartner or a friend of yours who is an English major, let's say, that will be the most effective way to get the message across. It's easy. I've seen it for, a reporter to talk to someone, an expert, and the expert to really delve into the details and the jargon, and then it all gets lost and the reporter's not sure what to make of it.
Yeah, so I do agree. I did met a few misunderstanding of my results. People were saying that N95 were evaluated at 0.3 micrometer. And then they were saying that it doesn't really filter out particles below that, but that is wrong. So typically, 0.3 micrometer is typically the lowest efficiency in terms of the size window. But N95 receptors are more effective if you're trying to remove smaller particles. So I think I did also see a few videos, nice sketch, trying to explain the mechanism in there. I think in the research, we did need these interpreters to transfer these scientific jargons or terminologies into something that people can understand.
I think for science communication, for a plug for geospatial and mapping, I've just seen like a huge increase in dashboards and maps, whether it's open source or ArcGIS, Esri, like online, and that's been a great way to kind of communicate and like have people be able to like play with the data. And I've had to like sit through a lot of their training videos to, as Dr. Mars said, to like keep it simple, stupid. So like, just making sure that's not, don't want to create a dashboard that's all cluttered and like, ugly and people don't know where to look. So that's like pretty challenging.
Yeah, and I'll follow up with that, what Dr. Haas just mentioned about talking to the media. I had several opportunities here at South Carolina to talk to media in Columbia. And it's true, when we are talking to the reporters, they actually guide you through the questions so that you stop talking about jargon to the point that the audience won't understand. So it's really a good opportunity. And I think it also points out just how to present it to people, to general public, so that they don't get bored listening to all the science you have done, but at least get to the results right away. And as Young mentioned, you have to be careful about how you say it, otherwise you get misinterpreted, and that can become a problem. So that's something you do have to be careful about. And that's where I think the reporter whom you're talking to can come into play to make sure that the communication is right.
Often the reporters can be actually very well informed. So it can be a different experience than working, with the communities and involving them as well. Maya, do we have another question from the Q&A?
Sure. How risky is the fomite route relative to other transmission routes? That was for Dr. Hope or anyone else. It came in during Dr. Hope's presentation.
I think it boils down to the type of fomite, and there's much more to learn about it. So in this particular case, we have to understand that the transmission is there in the air, and then it has to get to the fomite. So I guess I'll pass it on to our risk analyst expert here, Haas, to get into that a little bit more. But we have to understand that all of these routes play a role, and until we find out, I don't think we can specify that one particular part actually dominates.
So there have been very, very few instances reported that could be attributable to fomite transmission. I came out with a Twitter stream maybe a couple of weeks ago on this. I think, the inhalation route is much more thoroughly documented. In the healthcare setting, the ballistic impact route is certainly documented, but at best, we only have really 2 or 3 case reports or incident reports that appear to be fomite connected. So it's certainly not zero, but it's probably very, very small compared to the other routes.
All right, I see a question here, make me curious as well. Many people have been wearing masks covering their mouth, but not their nose. In terms of aerosol transmission, is there any information on how effective this is in terms of giving and receiving virus?
That's a good question. We don't know. I can say that when people are just breathing, they produce 10 times fewer aerosols on average than when they're talking. And some of that breathing could be happening through the nose. I would say, yes, some of the aerosols are generated when we're talking from our lips coming together and the film breaking and bursting, a film of saliva. And so obviously if you're breathing through your nose, then that's not happening. But of course, if you're breathing through your nose and you're wearing a mask, then you're not getting any protection. You know, it certainly helps block aerosols that you may be generating when you talk, and maybe a smaller amount that comes out of your nose from breathing. But it's, you know, you're probably, if you're wearing it down over you have your nose hanging out, then you're probably breathing through your nose. And again, you're not getting the protection. And so it's suboptimal. And so as a result, in all my interviews now, I've been, for the past couple of months, I've been saying, you know, whenever I say wear a mask, I say wear a mask covering your nose and mouth.
Right.
And I think that if the mask only covers the mouth area, maybe there will be more leakage as well. If you're trying to inhale or exhale with your mouth.
All right, thank you. Maya, do we have another question from the list?
Sure, we have one asking about the sewage. So wanting to know if going into or around sewer manholes is like how risky is that to avoid for your exposure to COVID-19, and similarly for storm sewers. And then there was a follow-up question too for Dr. Naughton, I think similarly. What does the research show? What does the research show in terms of COVID-19 and wastewater and your potential exposure?
Yeah, I mean, I think Dr. Haas can go first.
There's yet to be any report of viable virus in wastewater. And at this point, the recommendations, and there was just a Water Environment Federation Blue Ribbon Committee report on this. The recommendation is that the ordinary PPEs that wastewater treatment operators and sewer workers use are sufficient for protection. But like any other area of science, this may change if the isolation of the virus is found to occur.
Yeah, but what Dr. Haas said, and they have found, there's been some studies in China finding it infected like in the stool, but SARS-CoV-2 is like rapidly degraded with temperature and humidity, like by the time it gets through the sewer pipe and gets diluted. So probably very like minimal exposure, but people collecting samples wear proper PPE. I mean, some universities are requiring like even the Tyvek suits or things when they're collecting the sample, and same with the treatment workers, making sure that they are protected when they're working in different stages of the treatment. So there has been previous studies with SARS-CoV-1 and even SARS-CoV-2 about some issues when you don't have very good plumbing in your building, and the aerosols, toilet aerosols are coming up, and Amoy Gardens was a big study. But again, it's very kind of like minimal compared to the aerosol route and what, you know, Dr. Marr has been focusing on. So, but please, you know, close the lid on your toilet when you flush, not just for SARS-CoV-2, but for other pathogens. It's just better that way.
All right, thank you. I think we have time for one more question. So there's one here I see that seems like a way to close here. So not because the science is not valid, but due to skepticism and lack of trust of science. I think that this is a crisis that is for many scientists of different backgrounds. So how do we know how well we're actually reaching the public, given that so much skepticism and lack of trust that exists out there for science?
So again, I mean, I'll plug the entire field of risk communication, which, you know, I certainly have no expertise in, but I'm aware of the field. You know, there is a literature on barriers to people acting based on scientific information in other contexts. And we really need more detailed risk communication studies to understand those barriers in the context of SARS-CoV-2. And so that question itself can be approached scientifically. And I think it's ripe to do so, obviously, in collaboration with other experts outside the AEESP community.
All right, well, I think it's time that we brought this to a close. That's part of my job here, is to make sure we end on time. So today we heard.
Dr. Stewart, I think we still have a time for another question.
Okay, sure, great.
Oh, I didn't queue one up, but there have been questions on the masks, and so two are: one, are there new materials being developed that are affordable, that that are more easier to be heard through, and then also in terms of disposal of masks, people are seeing them washing up on beaches and so on, and so just sort of, could you comment on that?
So I think for the new materials on masks, there's quite active research going on in the materials field. But in terms of maximizing the voice through the mask, I think it might people might want to consider about some microstructures that can basically magnify the sound wave through the mask. But I'm not an expert on this area. People can put more thoughts on that. So in terms of the disposal of these masks, if people use cloth masks, then these cloth masks can be washed, and washing and drying doesn't affect the filtration efficiency. But in terms of the surgical mask or N95 respirators, these disposals have to be sanitized, have to be cleaned. And I would say that the processing would be quite similar to the common air filters or furnace filters, because they use similar materials in there. So I would say it is definitely going to be an issue post-pandemic, because people consume a lot of these surgical masks during this time.
And I think we have another question we could take, and there was a question asking about what are your recommendations for opening up, since many of us are going back or have been still at work. And so what would you recommend as some of the best ways to be safe?
I'd say look at that Swiss cheese model and practice as many of those layers as you possibly can in your activities.
Thanks, Dr. Hess. Dr. Stewart, over to you.
All right, thank you. All right, so in closing, so today we have heard some very interesting work related to virus aerosolization and transmission from common everyday sources and activities, as well as the effectiveness of protection and control measures we individually and collectively take. We also saw how Drs. Marr, Naughton, Wang, Hoke, and Haas were able to quickly transition and apply their environmental engineering and science expertise to addressing the real and urgent needs for solutions for the COVID-19 pandemic. Furthermore, they have provided us with examples of ways that we can all disseminate our knowledge to the public and inform better decisions and actions at many levels. So let me say thank you again to all of our speakers for the work that you do and for graciously agreeing to share your experiences and your insights with all of us today. I'll conclude with a challenge and a quote related to fostering informed decisions and actions. So the challenge to us all is the following. As we continue learning and pushing the boundaries of science and technology, we must also continually try to find new ways of involving stakeholders and the public in a two-way communication that is ultimately needed to ensure that the solutions we develop can truly enable more impactful, equitable, and wise decisions. And my final quote from a wise scientist and teacher, or at least attributed to Galileo Galilei, which I've slightly updated for the times, is you cannot teach people anything. You can only help them discover it in themselves. Thank you. And with that, I'll turn it over to Maya for some final words.
Thank you, Dr. Stewart, and thank you to everyone who has participated, presented, and watched and sent questions in. So just follow up that we do have a quiz associated with each session, and you can go on our website or scan that QR code to take it. There's a certificate that you get at the end of all 6 quizzes. And for those of you who are Envision ENVSPs, this counts as continuing Envision education credits. And so do send an email to us that you have completed. For next week's session, we go on to session 3, and it's about COVID-19 and the creation of efficient, healthy, and resilient cities. I'd like to say thank you for attending. We have a large group of folks who are behind the scenes here, students at both the University of South Florida and at UC Merced, and also staff with the Strong Coast program. So thank you to our sponsors and everyone who's been involved today.